So what if I had the reaction calcium plus HBr, this is an aqueous solution, and it yields CaBr2 in aqueous solution plus hydrogen, which is H2 gas. So this is the reaction. And what if I asked you, I want you to do three things. First, I want you to write this as an ionic equation, net ionic equation. And then I want you to write the half reactions, the redox half reactions. So the easiest way to write the half reactions is to first start by writing the ionic equation. Remember, we talked about that. We did a lot of these kinds of problems actually back when we worked the net ionic equations in when we were doing acid bases. So what you do is for the ionic equation, what you do is you go species by species and you go and you break it apart if it's in water and you go figure out what the charges on everything is going to be. Well, this is a solid. It's not an aqueous solution. Okay, it's just some calcium powder. So that just stays the same, CaS. Okay, but this HBr, this is an aqueous solution. And there's a 2 in front, so I need to carry that. Hydrogen always wants to have a plus charge, so I'll put this in aqueous solution. This 2 applies to the Br, to the bromine. And bromine, if you look at the periodic table, it's always going to want to have a negative charge like this. Okay? So that's on the left-hand side of the equal sign. On the right-hand side of the equal sign, I have CaBr2. So I have 1 calcium, and the charge on calcium from the periodic table, if you look at it, is plus 2, aqueous solution. But here I have Br2. There's 2 bromine, so I need to carry that with a 2. Br. Bromine always wants to be negative. And then I have my H2. This is not an aqueous solution, so it's H2 gas, just stays the same. So this is sort of like the first step in a lot of these problems. You'll be given a reaction. First thing is write an ionic equation for this reaction. And we've done this in previous sections. I told you to review that. I'm doing it again here. Calcium remains. The hydrogen gives you H+. I have 2 of them because of this. The bromine, I have 2 of them because of this coefficient. It wants to be a -1. The calcium wants to be +2. I have 2 bromines, so I have 2 bromines, and each one wants to be -1. The hydrogen gas, it's no charge because it's not in any kind of solution. It's not dissociating. So that is what we call the ionic equation. So the next thing I want to do is I want to find what we call the net ionic equation. So in order to find the net ionic equation, you just look at the ionic equation and you figure out what is common on both sides of the equal sign, or the yield sign. And if you look, this 2-bromine here also exists on the other side. So that means that the calcium, the hydrogen, end up changing into what's going on over here. Notice the H+ becomes hydrogen gas. Notice the calcium becomes calcium ion. But the 2 bromines with the negative charge and the 2 bromines with the negative charge, they exist on both sides of the yield sign. So that means that we learned all this before, that those are spectator ions. Those are ions that are just hanging around the solution, but they're not actually participating in the reaction. So when you go from ionic to net ionic, you just take away the spectator ions. So what you have is Ca, calcium, plus 2 hydrogen ions, aqueous solution. And then what you get is calcium plus H2. Okay, so this is the net ionic equation because I broke down everything, but I figured out that one of these things really didn't do anything. It's just hanging around, doesn't participate or change. So this is really the net ionic. This is really where the rubber meets the road of what's really changing in this reaction and what's really doing anything as far as electron transfer. Now the part C, the part that we really want to get to, is the half reactions. Now that we have the net ionic equation, we can more easily write the half reactions down. Okay? We can more easily write the half reactions down. What is calcium doing? Calcium is neutral, but then it has a positive charge over here. The only way that it can have a positive charge is if it loses electrons. So the calcium goes from being neutral to being an ion. So I'll write it like solid. Calcium's a solid. It goes to being a positive ion, but in order to do that, it has to give up 2 electrons. Okay, so I write that in the half reaction. Calcium goes to this, has to give up 2 electrons. Now let me go over here. The hydrogen, let me switch colors. Hydrogen, I start out with 2H plus. Notice I'm using the coefficient. I'm using what I have in my net ionic equation, okay? I have 2 hydrogens like this, which are in aqueous solution. And it ends up going into being a stable atom, okay? So the only way that it can go into being a stable atom is if it gains electrons, and it's going to gain 2 electrons because I have 2 hydrogen ions to begin with. And then I'm going to get H2 gas. Make sure you understand this, okay? All I'm doing is I'm taking the net ionic equation and I'm looking at what's changing and I'm writing down the loss of electrons and the gain of electrons. So what's happening over here, really, this calcium has lost electrons. So I've lost electrons, and because of that, we call this oxidation, right? And because this hydrogen's gained electrons, we call this reduction. So if on a test or a quiz, your teacher says, here's an equation, I want you to write the oxidation half reaction and the reduction half reaction, and I want you to, circle those or whatever. Tell me which one's oxidized and which one's reduced. So then you'll go and look at that and you'll say, all right, first thing I'm going to do is take this reaction if it's given to you in this form. A lot of times the reaction will be given to you like this, but in this case, the reaction is given to you like this. First thing you do is break everything apart. Calcium goes here, 2 hydrogen wants to be +1 here, 2 bromines want to be -1 here, calcium wants to be +2, bromine, I have a 2 because of the subscript, wants to be -1, hydrogen stays the same. Okay, now how do I write the net ionic equation? The bromines go away because they're common on the left and the right. This is the net ionic equation. So this is your net ionic equation of what's really changing and happening in this reaction. So then I take this net ionic equation and I further break it into half reactions. The calcium yields and becomes a calcium ion with a charge of +2. The only way it can do that is if it gives up 2 electrons. So I write it like that, and because it gives up electrons, I call it oxidation. The 2 hydrogen ions that I had in my reaction, notice I'm keeping the coefficient here, they become hydrogen gas, H2, and the only way that can happen is if 2 electrons combine with it to make it neutral, and since I have 2 of them like this, each hydrogen atom requires 1 electron to become neutral again, and since I've got 2 hydrogen ions to begin with, and I make them each neutral like this, then I'm going to get H2 gas. So that's what I get there. So this is the oxidation half reaction, this is the reduction half reaction, and notice that unlike the last problem, in this problem, I have 2 electrons that are lost, and then I have 2 electrons that are gained by the hydrogen. So what's really happening in this reaction is the calcium is giving up 2 electrons, and the hydrogen here is really gaining 2 electrons. So the calcium's liberating and getting rid of electrons, and the hydrogen is taking them in, and that's how this reaction is happening. So this is crucial material for you to understand. Half reactions is very important because when we balance redox reactions, the way it's going to go down is we're going to give you a reaction and it's not going to be balanced, and we're going to say balance this redox reaction. So you're going to have to break it into half reactions, and we're going to do some stuff that we'll learn later on, and you'll end up combining them back together. We didn't do that part here, but you'll end up combining them together to balance the reaction later on. So this section of this course is just teaching you how to take an oxidation reduction reaction and break it into half reactions. In this case, here is the net ionic equation, and we break it down into these 2 oxidation reduction reactions here. And then in another case, we have this kind of reaction here. We know that we're losing electrons, we know that we're gaining electrons, and we break it up into an oxidation process where we're losing electrons and into a reduction process where we're gaining electrons. The main thing you want to make sure of is that the electrons lost have to equal the electrons gained. And in the process of doing a lot of problems as we go forward, what you're going to find is that when you balance these things, you need to make sure that through the math, that you make the electrons lost equal the electrons gained. So that closes the section out on half reactions. Make sure you understand how to do it. Make sure you understand the concept. Taking the reaction, breaking it into an electron loss and an electron gain. That is the process of writing down half reactions. When you circle the half reaction on your test, you want to make sure the electrons lost is equal to the electrons gained. even if you have to take one of these equations and multiply by a number. Here we had to multiply by 2 to get this to happen, but over in the other equation, we didn't have to actually multiply by anything because we had it balanced, and once we had it all balanced, the electron transfer was already set up for us. But in the future, we're going to have situations where nothing's balanced, and it'll be up to you to balance that electron transfer. So follow me on to the next section, where we will continue talking about redox reactions and how electrons are gained and electrons are lost. And I think as you follow me along, we'll get into these situations where we can balance these reactions, these more complicated reactions, using the redox methods, the cornerstone of which is that these electrons have to balance. When you lose some electrons, you have to gain the same number of electrons in the reaction somewhere.